Hi folks, I'd like to now go through the solution for one of the textbook problems. So we're going to look at page 25, number 19. So let's take a look at the question here. We have a child with a mass of 35 kilograms is sitting on a swing attached to a tree branch by a rope 5 meters in length. Child is pulled back 1.5 meters, measured horizontally. So we're looking for the horizontal force that will hold the child in this position. So one thing that should be telling us here is that we have a situation of equilibrium. So if the child is being held in this position, means it's not moving, meaning our net force is equal to 0. And then we want what is the tension in the rope. Okay, so as usual here, what I'm going to do is I want to draw out my situation before I try to draw a vector diagram. Okay, so I have a rope here, okay, 5 meters long that is being held back. Okay, so the rope itself is 5 meters. It's being held back 1.5 meters from the horizontal. Okay, so that means this distance here is 1.5. Okay, and I've got my object that's being held here. So let's take a look at the forces that are acting on this object. Okay, so as usual, we have the force of gravity pulling it down. Okay, we have the tension in the rope pulling on it, so there's another vector, and then we've got someone pulling the swing back, holding it into position. So these are the three forces that are acting on the object, and since the object is not moving, it's in equilibrium, these three forces must add up to 0. Okay. Now again, this is my situation that shows all the forces acting on the object. This is not what I'm going to use to calculate what I'm asked to calculate. I'm going to draw a vector sum diagram right now. One thing I noticed is that two of these vectors act at 90 degrees of each other, so that's helpful. I'm also told that the child is, and I guess the child plus swing are 35 kilograms. So here we have 35 times 9.8, so we can calculate that force. So 35 times 9.8, okay, 343 newtons. Okay, so let's draw this here. Let's start with this vector going down. Okay, so again, this is the force due to gravity, and we know that its magnitude is 343. Now I've got the force that's being applied horizontally to keep it in position, so I don't know anything about that yet other than it's being applied horizontally. And since the object is in, so one thing I will say here is that we notice these two vectors are perpendicular to each other, so do we have a 90-degree angle here? And since it's in equilibrium, my last vector, the tension in the rope, has to close off this triangle. Okay, so these are my three vectors that add up to the 0 vector. Okay, we'll call this FR for the rope. Okay, now one thing we are missing is the direction of this vector here, and this is where now we can use the other information that's given, because we have information about a right angle triangle. So I can determine this angle here we'll call theta. Since it's a right angle triangle and I know two sides, I can just use the trig ratios. So here I know the adjacent and hypotenuse sides of that triangle, so I can just use cosine. So cosine of theta is 1.5 over 5, and so theta is cos inverse of 1.5 over 5. So let's calculate that here. Again, please make sure if your calculator does not open up a bracket when you use the trig ratios that you do it yourself. So 1.5 divided by 5, okay, and that's 72.54. So I know that this angle here is 72.54 degrees. Okay, and because it's a right angle triangle, I can just again use the primary trig ratios. Okay, So let's do that. The first thing they ask us to find is the horizontal force which will hold the child in this position. So that'll be FH. And we see here that, well, here's our angle. We know the adjacent. We're looking for the adjacent side. We know the hypotenuse. So again, we'll use cosine. So cosine of 72.54 degrees is equal to FG, which is 343. Oh, and I just realized that was a very silly mistake. That's not the hypotenuse side. It is the opposite and adjacent side. So let's try that again. Tangent. Okay, so always make sure you're paying attention. Okay, so here we've got opposite and adjacent. We'll be using tangent. Okay, so tangent of this angle is the opposite side, 343 over the adjacent, which is the one I'm looking for. Okay, sorry about that, folks. And so let's just calculate this quickly. So we got 343 divided by tan of 72.54. Okay, so let's do this here. I got 343 divided by tangent of 72.54 is equal to 107.88. So the magnitude of FH is equal to 107.88 newtons. Okay. So we can say that FH is equal to 107.88 newtons. Okay. In the horizontal direction. And based on my drawing, I'm going to the right, toward right. Okay, so again, this is based on the way I drew the situation. Had I drawn it on the other side, meaning the person is holding it on the other side, it would be toward the left direction. Okay, the next thing I want to determine, though, is the tension in the rope, and that would be this force here. In other words, this force in my vector diagram. So let's do that here. So now we've got, well, let's use opposite and hypotenuse again. Better to use the exact number as opposed to the approximate number that we determined for FH. So here, let's use sine of 72.54 is equal to the opposite side, 343, over the hypotenuse, which is what I'm looking for. Okay, and so the magnitude of FR is 343 over sine of 72.54. So let's calculate that here. So 343 divided by sine of 72.54, which is equal to 359.57. Okay, so we can say that FR, the tension in the rope, is equal to 359.57 newtons. And to describe the direction, well, it's 72.54 degrees above the left horizontal. Okay, so 72.54 degrees above the left horizontal. Okay, and there you have it.